Everything you think you know about space is probably wrong. We are about to dismantle 30 of the most stubborn cosmic misconceptions, from the color of the sun to the reality of alien life. By the end of this journey, you will possess a clear and scientifically accurate picture of our universe. We will uncover why black holes are not cosmic vacuum cleaners and whether a human body truly explodes in the void. What is the one space fact you are most certain about? Our very first stop on this journey of cosmic truth begins with the star at the center of our own solar system. Look up at the sky on a clear day and you will see a brilliant yellow orb beaming down. This seems like the most undeniable fact of all. The sun is yellow. But this is our first great illusion, a trick played on us by our own planet. The sun, in the pure vacuum of space, is not yellow. It is, in fact, a blinding white. Think about the light from a standard light bulb. We call that white light. The sun is a massive ball of incandescent gas emitting light across the entire visible spectrum, which together our eyes perceive as white. So why does it look so different from down here? The answer lies in our atmosphere. When sunlight enters our sky, it collides with molecules and tiny particles. Blue light, with its shorter wavelengths, gets scattered far and wide in every direction. This scattering is what paints our daytime sky blue. The light that reaches your eyes directly from the sun, however, has been stripped of much of its blue. What remains is the longer wavelength light, the reds, oranges, and yellows, creating that familiar golden glow. For absolute proof, we only need to look at photographs taken by astronauts in space. Their images show the sun as a stark, featureless, and overwhelmingly white circle against the blackness of the void. There is even a fleeting phenomenon on Earth that reveals this hidden truth. During a very clear sunset, just as the last sliver of the sun dips below the horizon, you might, if you are incredibly lucky, witness a green flash. This burst of emerald light is the final, extreme result of atmospheric scattering, briefly separating the colors and offering a ghostly glimpse into the sun's real composition. So the next time you draw the sun, a yellow circle with lines radiating out, remember you are drawing a beautiful lie, a testament to the filter we live under. This same trick of perception applies to another celestial body we see every night. You have likely heard of the dark side of the moon, a phrase that conjures images of a hemisphere locked in perpetual and mysterious shadow. This is our second cosmic myth, and it could not be further from the truth. The moon does not have a permanent dark side. It has a far side, a part we simply never see from Earth, and that far side is bathed in sunlight just as often as the side we know. The reason for this is a beautiful and precise cosmic dance known as tidal locking. Our moon does, in fact, rotate on its own axis. If it did not, we would eventually get to see all of its surface. But its rotation is perfectly synchronized with its orbit around our planet. It takes the moon about 27 days to complete one full spin, and it also takes about 27 days to complete one full circle around Earth. This means the same face is constantly turned toward us, like a ball on a string that you swing around your head, always showing you the same painted spot. Now think about what this means for sunlight. As the moon travels around Earth, the sun illuminates it from all directions. When we see a new moon, the far side is drenched in daylight. When we see a full moon, the near side is lit up and the far side is in darkness. The far side experiences 2 weeks of continuous daylight followed by 2 weeks of profound night, a day-night cycle just as extreme as the one on our familiar lunar face. So the next time you look up at the full moon, remember that on the other side, the sun is setting, beginning a long, cold night. It is not a realm of eternal darkness, but a landscape of regular and dramatic change, forever hidden from our direct view, yet fully participating in the light of the sun. Mercury stands as the planet closest to the sun, a scorched world orbiting just a few dozen million miles from that inferno. It seems only logical that it would hold the title for our solar system's hottest planet, but this is a perfect example of logic being betrayed by reality. Mercury is not the hottest planet. That crown goes to Venus, a world nearly twice as far from the Sun, shrouded in a beautiful but deadly atmosphere. The difference lies not in proximity, but in insulation. Mercury is a barren rock, airless and exposed. Its sun-facing side does indeed become brutally hot, with temperatures soaring to around 800 degrees Fahrenheit during its long day. But without an atmosphere to trap that heat, the energy simply radiates back into space as soon as that side rotates into darkness. The nighttime temperatures on Mercury can plummet to nearly 300 degrees below zero, a swing of over 1,000 degrees that reveals its fundamental inability to hold onto warmth. Venus tells a completely different story. It is wrapped in an incredibly thick, suffocating blanket of carbon dioxide with clouds of sulfuric acid. This creates a runaway greenhouse effect of staggering efficiency. Sunlight passes through the atmosphere and heats the surface just as it does on Earth. But when the surface tries to radiate that heat back outward as infrared radiation, the dense carbon dioxide traps it. The heat cannot escape. It builds and builds, turning the entire planet into a constant global oven. The surface temperature on Venus is a consistent 860 degrees Fahrenheit, day or night, at the equator or the poles. That is hot enough to melt lead, and it decisively surpasses even the sunniest afternoon on Mercury. This dramatic comparison holds a profound lesson for understanding planetary climates. A world's atmosphere is not just a layer of gas, it is a thermostat, a thermal blanket that dictates its ultimate fate. The story of Venus shows us that a planet's temperature is not simply a matter of its distance from a star, but a complex result of the air it keeps. Another belief so widespread it feels like a universal truth is that the Great Wall of China stands as the one human structure visible from space. This idea suggests a monument of such immense scale that it carves a solitary line across the planet, a testament to human achievement visible even from the void. Yet this powerful image is a complete fiction, shattered by the cold, hard physics of human vision and orbital perspective. The wall is not, and has never been, visible to the unaided human eye from space. The fundamental problem is one of scale and contrast. From low Earth orbit, where the International Space Station flies at an altitude of around 250 miles, the Earth is a vast and complex canvas. An astronaut looking down sees continents, weather systems, and the deep blue of the oceans. To make out the Great Wall, your eye would need to resolve it as a distinct object against its background. This comes down to a concept called angular resolution, which is the minimum distance between 2 points that your eye can still perceive as separate. The Great Wall is wide, averaging only about 30 feet across, with its materials blending into the natural colors of the soil and stone around it. From orbit, its width translates to an angular size far, far smaller than the resolving power of the human eye. It is like trying to see a single human hair from a distance of 2 miles. You simply cannot do it. From that incredible height, the wall merges into the landscape, becoming an indistinguishable part of the terrain. In reality, astronauts report that what they can see from orbit are massive city lights at night, the geometric patterns of large-scale agriculture, and sometimes the gleaming surfaces of major airports. These features have the size and contrast to be visible. The Great Wall, for all its historical grandeur and length, simply does not. This has been confirmed by numerous astronauts, including Chinese astronauts themselves, who have stated they could not see the wall without powerful telescopic lenses. The myth likely originated from a much older and equally incorrect idea that it could be seen from the moon. That notion is so easily dismissed it barely needs debunking. From the lunar surface, the entire Earth is a beautiful blue and white marble, roughly the size of your thumbnail held at arm's length. No human structure at all is visible from that distance. So the next time you hear this claim, you will know the truth. The Great Wall is a marvel of human engineering, but its true scale is a terrestrial one, a reminder that our greatest achievements are still humbled by the sheer immensity of our own world. Perhaps the most terrifying image in all of science fiction is that of a black hole, a relentless cosmic vacuum cleaner sucking in everything in its path, from stars and planets to the very fabric of space. This vision of inevitable doom, however, is a profound misunderstanding of how gravity truly works. A black hole is not a cosmic hoover, endlessly pulling matter into its gullet. Its gravitational pull is in fact no different in kind from that of any other massive object. It obeys the same universal laws that keep Earth in orbit around the Sun. The key to understanding this lies in two critical concepts: the Schwarzschild radius and the event horizon. Every object with mass has a Schwarzschild radius, a theoretical boundary where the escape velocity would equal the speed of light. For our Sun, this sphere would be less than 2 miles across, buried deep within its core. For Earth, it would be the size of a peanut. These objects are not black holes because their physical size is vastly larger than their Schwarzschild radius. A black hole is simply an object that has collapsed so completely that its entire mass lies within this boundary. The surface of this sphere is the event horizon, the point of no return. It is not a physical surface you could touch, but a mathematical threshold. Outside of this boundary, the gravity is powerful, but it is still just gravity. This is beautifully demonstrated by computer simulations and the mathematics of orbital mechanics. Just as a spacecraft can maintain a stable orbit around Earth or the Moon, an object could, in theory, orbit a black hole perfectly safely, provided it stays well outside the event horizon. The gravity would be intense, and you would experience extreme tidal forces if you got close, stretching you like taffy, but you would not be inexorably sucked in. If our Sun were to be instantly replaced by a black hole of exactly the same mass, a truly chilling thought experiment, the orbits of all the planets would remain completely unchanged. We would be plunged into eternal night and frozen solid, but Earth would continue its same elliptical path year after year because the central gravitational source, the mass, has not changed. The vacuum cleaner myth arises from imagining the black hole as an active force when it is really just an extreme concentration of mass. You are only in danger if you venture too close, crossing that final threshold where the universe's speed limit is no longer enough to save you. The true terror and wonder of a black hole is not that it sucks everything in, but that it marks a place where the normal rules of reality simply cease to apply. Hollywood has painted a gruesome and dramatic picture of what happens to an astronaut who finds themselves unprotected in the vacuum of space. The body instantly freezes solid, shatters, or violently explodes in a cloud of ice and gore. This cinematic spectacle, while unforgettable, is pure fiction. The reality of exposure to space is far more strange and medically precise, a rapid and brutal series of physiological failures, but not an explosion. Your body would not pop like a balloon. The vacuum of space is not pulling you apart with immense force, but rather, it is the absence of pressure that allows processes inside your body to run wild. The most immediate and startling effect is a phenomenon called ebullition. Here on Earth, liquid boils when its vapor pressure equals the surrounding atmospheric pressure. At high altitudes, water boils at a lower temperature because the air pressure is lower. In the complete vacuum of space, the pressure is zero. This means the boiling point of your bodily fluids, which are mostly water, plummets to below your own body temperature. The saliva on your tongue would instantly begin to boil. The moisture in your eyes, your skin, and the fluids surrounding your soft tissues would start to fizz, not with heat but with the sudden lack of pressure. You would not feel hot, however. In fact, the evaporating moisture would cause rapid cooling. Your body would not freeze instantly, as space is a vacuum and therefore a fantastic insulator, but the areas where fluids are boiling would cool down significantly. Simultaneously, you would experience excruciating decompression. The gases dissolved in your bloodstream, mainly nitrogen, would rapidly come out of solution, creating bubbles throughout your circulatory system, a condition akin to the bends that deep-sea divers experience, but happening in seconds and on a catastrophic scale. Your circulatory system would begin to fail. Despite this internal turmoil, your skin and circulatory system are resilient enough to hold you together. You would not explode. Your body would swell to perhaps twice its normal size as gases expand, but your skin and tissues have enough tensile strength to contain the pressure. The most critical countdown, however, is the one for oxygen. Within 10 to 15 seconds of exposure, the oxygen stored in your blood would be depleted. Your brain, starved of this vital element, would shut down. You would lose consciousness. This is the point of no return for an unprotected human. From there, brain death would follow within 1 to 2 minutes. There are sobering real-world incidents that inform this grim understanding. In 1971, the 3 Soviet cosmonauts of the Soyuz 11 mission died during re-entry when a faulty valve caused their cabin to depressurize. They were not wearing spacesuits. By the time the capsule landed automatically, they were found in their seats, peaceful but lifeless, having succumbed to hypoxia in less than a minute. Their bodies showed no signs of explosion or freezing, only the telltale effects of rapid decompression. Even more telling was a NASA accident in 1965, when a technician testing a spacesuit in a vacuum chamber had his helmet accidentally depressurized. He remained conscious for about 15 seconds, later recalling that he felt the saliva boiling on his tongue before he passed out. The chamber was repressurized within a minute, and he survived, making a full recovery. These events paint a clear and harrowing picture. The true danger of space is not a cinematic burst, but a silent, swift, and systematic suffocation, a battle your body is fundamentally designed to lose. Science fiction films have trained us to see the asteroid belt as a chaotic junkyard, a swirling maelstrom of colliding rocks where any spacecraft would need to dodge and weave for its very survival. This vision of an impassable obstacle course is another myth that dissolves under the stark light of real data. The reality is one of profound emptiness, a void so vast that navigating it is one of the least of a mission planner's concerns. The main asteroid belt, located between the orbits of Mars and Jupiter, contains millions of objects, which sounds impossibly crowded until you consider the sheer volume of space they occupy. This region is a cosmic frontier spanning billions of cubic kilometers. If you were to stand on the surface of an average asteroid, your nearest rocky neighbor would likely be millions of kilometers away. That is a distance farther than from the Earth to the Moon. In fact, the average separation between substantial asteroids is so great that you could fly a probe through the entire belt and have a probability of collision so close to zero it is not even worth calculating. We have done this not once but many times. Spacecraft like NASA's Dawn mission, which visited the protoplanets Vesta and Ceres, spent years traveling through the heart of the asteroid belt. Its path was not a frantic slalom, but a serene, straight-line cruise. Mission controllers did not plot elaborate courses to avoid impacts. They simply aimed for their targets, confident in the staggering emptiness. The Pioneer and Voyager probes, on their grand tours of the outer solar system, passed through the belt without a single close call. The idea of a dense field is a dramatic compression, a necessity for storytelling that bears no resemblance to the true, silent expanse. The true danger in the belt is not from a chance collision, but from the immense loneliness and the vast distances that separate one fascinating world from the next. Each asteroid is an island in a sea of nothingness, a reminder that even in a crowd of millions, the universe is mostly made of space. This persistent myth about black holes as cosmic vacuum cleaners often goes hand in hand with another common fear, the idea that space exploration is a massive drain on public funds. Many people are convinced that agencies like NASA consume a colossal portion of the national budget, diverting money that could be spent on Earth. The reality of the numbers, however, tells a completely different story. NASA's annual budget is not a gaping hole in the federal treasury. It is a remarkably small investment in our future. For every dollar the United States government spends, less than half a penny goes to NASA. To put that in perspective, imagine the entire federal budget as a $100 bill. NASA's share would be about 50 cents. Compare that to the more than $15 that would go to the military, or the nearly $25 allocated for major health programs. The space agency's funding is a tiny sliver of the whole, a fraction of a single percent. This misconception has real consequences, shaping public opinion and political debates. When people believe space exploration is wildly expensive, they are more likely to see it as a luxury we cannot afford, rather than a vital investment that yields immense returns. The technologies born from space research are everywhere around us. The cameras in your smartphone, advanced medical imaging, water purification systems, and even memory foam mattresses all have roots in NASA innovations. Beyond these tangible products, space science drives our understanding of Earth's climate, inspires generations of scientists and engineers, and fulfills a fundamental human drive to explore and understand our place in the cosmos. The next time you hear someone claim we are spending too much on space, remember that 50 cents on a $100 bill. It is not an exorbitant cost, but a modest investment in knowledge, technology, and the boundless potential of the human spirit. Even the most rational minds can find themselves glancing at a full moon and wondering if something strange is in the air. For centuries, folklore has insisted that the lunar cycle holds a mysterious sway over human biology and behavior, triggering madness, driving up crime rates, and filling maternity wards. Yet this deep-seated belief, known as the lunar effect, crumbles under the scrutiny of cold, hard data. Scientists have conducted hundreds of studies, analyzing millions of data points from police reports, hospital admissions, and birth records across decades. The result is a resounding and consistent silence. There is no statistical link between the phases of the moon and increases in violence, psychiatric episodes, or the number of babies born. One major analysis examined over 100 separate studies and found the correlation to be precisely zero. So why does the myth feel so true? The answer lies not in the moon, but in the wiring of our own brains, specifically a mental shortcut known as confirmation bias. Our brains are pattern recognition engines, and we are particularly good at noticing and remembering events that seem to confirm our existing beliefs. If you believe the full moon causes chaos, you will vividly remember the one busy, crazy night you worked when the moon was full. You are far less likely to note the dozens of other full moons that passed without incident, or the chaotic nights that happened under a new or crescent moon. The confirming evidence stands out, while the disconfirming evidence fades into the background, creating a powerful illusion of a connection where none exists. This is compounded by the fact that the full moon is a dramatic and attention-grabbing event. When something unusual happens on that night, the moon provides a ready-made poetic explanation. The moon's genuine power, of course, is not a matter of belief. Its gravitational pull is the primary force behind Earth's ocean tides, a monumental physical effect that demonstrates its real influence. But that force is simply too weak and too constant to affect the small, contained systems of the human body or mind. The water in a single human being is minuscule and bound within tissues, utterly immune to the tidal forces that move entire oceans. So the next time you stand under the brilliant light of a full moon, you can appreciate its beauty for what it truly is, a magnificent celestial body that guides the seas but leaves our fates entirely in our own hands. Floating inside the International Space Station, astronauts appear to be in a world without gravity, a place where the very concept of up and down vanishes. This is perhaps the most visually powerful space myth of all, the idea that there is no gravity in space. The truth is far more fascinating. Gravity is everywhere. It holds our galaxy together, it keeps the moon in orbit around Earth, and it is the very reason the space station stays in the sky. The astronauts are not floating because there is no gravity, they are floating because they are in a state of continuous freefall. Think of a classic physics demonstration. If you drop a bowling ball and a feather inside a vacuum chamber where there is no air resistance, they fall at exactly the same rate and appear to float next to each other as they plummet. Now imagine a thought experiment. You take that vacuum chamber and you throw it sideways incredibly fast. Because the Earth is curved, the chamber falls toward the planet, but its forward speed is so great that the ground curves away beneath it at the same rate. It is perpetually falling but never hitting the ground. This is precisely what the International Space Station is doing. It is moving forward at about 17,500 miles per hour, a speed so tremendous that as it falls toward Earth, our planet's curvature drops away, creating a perfect, endless fall. The station and everyone inside it are all accelerating downward together, which creates the persistent sensation of weightlessness, a condition more accurately called microgravity. If gravity were truly absent, the space station would not be tethered to our world at all. It would simply fly off in a straight line into the depths of the solar system. Instead, gravity is constantly pulling it into a curved path, a balance of motion and attraction that we call an orbit. This same invisible force is at work everywhere you look. The Earth is held by the Sun's gravity, the Sun is held by the gravity of the Milky Way, and every galaxy is bound to others in a vast cosmic web. The void of space is not empty of gravity, it is saturated with it, an unseen architecture that shapes everything we see. The universe was not born in a fiery blast. The very name, the Big Bang, is a misnomer that paints a picture of a cosmic bomb detonating in a dark, empty void. That image is fundamentally wrong. The Big Bang was not an explosion of matter into space, it was the rapid expansion of space itself. Imagine the entire observable universe, every galaxy and star, compressed into an inconceivably hot, dense point, a singularity. Then, in a fraction of a second, space itself began to swell, carrying the nascent universe along with it. A powerful analogy is to picture the surface of a partially inflated balloon. Glue several small dots onto it, representing clusters of galaxies. Now, as you blow more air into the balloon, the surface area expands. Every dot moves away from every other dot. No single dot is the center of the expansion. The center is the entire growing surface. This is precisely how our universe works. We see galaxies rushing away from us in every direction, not because we are at the center of some explosion, but because the fabric of space between all galaxies is stretching. The most profound evidence for this event is not something we can see with our eyes, but something we can detect with sensitive radio telescopes. It is a faint, cold glow that permeates all of space, the cosmic microwave background radiation. This is the ancient afterglow of the Big Bang itself. When the universe was young and incredibly dense, it was a searing plasma, opaque and glowing. After about 380,000 years, it had expanded and cooled enough for atoms to form, allowing light to travel freely for the first time. That first flash of light, once brilliant and hot, has been stretched and cooled by the relentless expansion of the universe over billions of years. Today, it reaches us as a uniform microwave whisper, a fossil from the very dawn of time, confirming that our entire cosmos was once a much smaller, hotter, and denser place. The Big Bang was not a bang at all, but the beginning of everything, a silent, swift unfurling that set the stage for all that would follow. Our planet's annual journey around the Sun traces a path that is nearly a perfect circle, a fact that directly challenges one of the most stubborn beliefs about our changing seasons. Many of us carry a simple mental model that we are closer to the sun in the summer and farther away in the winter. This feels instinctively right, but it is completely backwards for half the world. The true architect of our seasons is not our distance from the sun, but the persistent tilt of our world. Earth spins on an axis that is not straight up and down, but leans over at an angle of about 23.5 degrees. This tilt is the master switch for our climate, a constant orientation as we travel our year-long circuit. Picture the Earth in its orbit with the sun at the center. The North Pole is always pointing in the same direction in space toward the North Star. In the month of June, the northern hemisphere is tilted directly toward the sun. The sun's rays hit this part of the globe more directly, concentrating their energy over a smaller area. The days are longer and the light has less atmosphere to travel through. This combination of direct rays and extended daylight is the recipe for summer's heat. At the very same time, the southern hemisphere is tilted away. The sun's rays strike it at a shallow angle, spreading their energy thin over a much larger area. The days are shorter and the light must slice through more air, leading to the coolness of winter. 6 months later, in December, the situation is perfectly reversed. Now the southern hemisphere basks in the direct glare of summer, while the north leans away into winter's chill. The most compelling proof against the distance theory comes from a simple orbital fact. Earth is actually closest to the sun, a point called perihelion, in early January. This is the heart of winter for the northern hemisphere. Conversely, we are farthest from the sun at aphelion in early July during the northern summer. The difference in distance is so minor, about 3%, that it has almost no effect on our temperatures compared to the overwhelming power of the axial tilt. This elegant celestial mechanism is why seasons are opposite in the two hemispheres, a global reality that the simple distance model could never explain. Our world's graceful lean gives us the rhythmic pulse of the year, a cycle of warmth and cold written not in our orbit's shape but in the angle of the light. Another myth that feels etched in stone is the idea that lightning never strikes the same place twice. This piece of folk wisdom suggests a kind of cosmic fairness, as if a storm has a memory and avoids repeating itself. The reality is that lightning is a simple, powerful force of physics, and it is profoundly indifferent to our sense of fairness. Tall, isolated, and conductive objects are not just likely to be hit once, they are preferred targets struck over and over again. The Empire State Building in New York City provides the perfect example. This iconic skyscraper is struck by lightning an average of 25 times every single year. It is not a case of bad luck, but a predictable outcome of its design, acting as a giant lightning rod that offers the path of least resistance for a massive electrical discharge. The next time you see a thunderstorm, remember that the highest point on the horizon is not safe from a second strike. It is an invitation for one. This understanding of atmospheric electricity does not stop at the edge of our world. We have witnessed lightning on other planets, revealing alien storms of unimaginable power. Jupiter, the solar system's giant, is a world of perpetual tempests. Its great red spot, a hurricane larger than our entire planet, crackles with lightning thousands of times more energetic than anything we see on Earth. The Voyager and Juno spacecraft have detected these colossal flashes, radio bursts and optical pulses that speak of a chaotic and violent atmosphere. Even Venus, shrouded in its thick clouds of sulfuric acid, experiences a strange and continuous form of lightning, a constant flickering within its toxic shroud. Scientists study these alien electrical storms to understand the fundamental principles of planetary atmospheres. By comparing the lightning of Earth, Jupiter, and Venus, we learn what conditions are necessary to generate these immense sparks. Is it the collision of ice particles in a water-based atmosphere like ours, or the turbulent friction of dust and droplets in an alien chemical soup? Each new discovery helps us build a more complete picture of how weather works across the cosmos, proving that the raw power of a lightning bolt is a universal phenomenon, striking wherever the atmospheric conditions are right as many times as it pleases. A comet blazing across the night sky looks like a celestial torch, its fiery tail stretching for millions of miles, but that flame is another cosmic illusion. Comets are not burning, they are ancient, frozen travelers, often called dirty snowballs, and their glorious tails are born from ice turning directly into gas. The heart of a comet is its nucleus, a lumpy, dark mountain of ice mixed with rock and dust. As this frozen core swings close to the sun, the intense heat causes the ices to sublimate, transforming from solid ice into a vast cloud of gas and dust without ever becoming a liquid. This cloud, called the coma, envelops the nucleus in a hazy, glowing shroud. But the sun's influence does not stop there. The solar wind, a constant stream of charged particles flowing from the sun, and the sheer pressure of sunlight itself, push this material away, sculpting it into the iconic tails we see from Earth. A comet does not have just one tail, it typically has two, each made of different material and pointing in slightly different directions. The ion tail, a straight and often blue stream, is composed of gas that has been electrified or ionized by the sun's ultraviolet light. The solar wind catches these charged particles and blows them directly away from the sun like a cosmic windsock. The dust tail is broader, softer, and often curved, made of tiny solid particles that are pushed more gently by the pressure of sunlight. This tail follows the comet's orbital path, creating a graceful arc across the solar system. The European Space Agency's Rosetta mission gave us an intimate look at this process, orbiting Comet 67P for 2 years. Its photographs revealed a world of breathtaking drama, with jets of gas and dust erupting from the nucleus's surface, feeding the magnificent tails. The spacecraft witnessed the comet's activity surge as it neared the sun and fade as it retreated, a direct observation of the solar-powered engine that drives these celestial visitors. So when you see a comet, you are not looking at a fire in the void. You are witnessing a magnificent evaporation, a frozen relic from the solar system's birth, being sculpted by the invisible hands of sunlight and solar wind into one of the most beautiful phenomena in the heavens. Our constant guide in the northern sky holds a reputation for unmatched brilliance, but this is a classic case of importance being mistaken for intensity. The North Star, Polaris, is far from the brightest star we can see. In the grand hierarchy of stellar brightness, it ranks as only the 48th most luminous in our night sky. Its legendary status comes not from its power but from its perfect placement. Polaris sits almost directly above Earth's north rotational axis, a point in the sky called the North Celestial Pole. Because of this, as our planet turns, every other star appears to wheel in a great circle around this fixed point. Polaris is the steadfast hub of the celestial clock, the one star that never seems to move. This immobility has made it an invaluable tool for navigators for thousands of years, providing a constant reference for finding true north. To truly appreciate this, picture a time lapse of the northern sky. Over hours, the constellations of the Big Dipper and Cassiopeia would swing in a majestic arc, tracing perfect circles, while Polaris remains pinned at the very center, a solitary pivot in the turning dome of night. Meanwhile, other stars utterly outshine it. Look south on a winter evening and you will be stunned by Sirius, the dog star, which blazes with a brightness more than 20 times that of our faithful Polaris. In the summer, Vega in the constellation Lyra shines as another brilliant beacon, clearly dominating the northern star in sheer radiance. So while Polaris may not win a cosmic beauty contest, it wins the prize for reliability, a lone, steady hand in the spinning darkness. A strange face stares out from the rust-colored sands of Mars, a monument carved by an alien intelligence. This was the electrifying claim that erupted in 1976 when NASA's Viking orbiter captured an image of the Cydonia region. The picture showed what looked unmistakably like a massive humanoid face, complete with eyes, a nose, and a mouth, gazing upward from the Martian desert. It was a story that captured the world's imagination, a tantalizing promise that we were not alone. Yet this iconic image, which launched 1,000 conspiracy theories, was not a message from another civilization. It was a perfect storm of low-resolution, dramatic shadows and a fundamental quirk of the human brain. The original Viking photo was a grainy, black and white shot taken from a great distance, with a low sun angle casting long, suggestive shadows across a natural landform. It was just a hill. The real proof came decades later when more advanced spacecraft like the Mars Global Surveyor arrived with powerful cameras. They flew over Cydonia again and again, capturing the area in crystal-clear detail. The new images revealed the truth in stunning clarity. The famous face was gone. In its place was an ordinary, wind-battered mesa, a rocky outcrop pockmarked by erosion and collapse. The symmetrical features dissolved into a chaotic jumble of boulders, ridges, and avalanche chutes. There were no eyes, no mouth, no grand design, only the random and beautiful sculpture of geology. This compelling urge to see a face in a random pattern has a name: pareidolia. It is a hardwired feature of our human psychology. Our brains are exquisitely tuned to recognize faces, a vital skill for social interaction. This system is so sensitive that it often fires when there is no real face present, finding familiar patterns in clouds, wood grain, or the surface of Mars. We see the man in the moon or the shape of a dragon in a cosmic nebula. The Martian face was a cosmic Rorschach test, a projection of our own hopes and fears onto a distant, rocky landscape. It was not evidence of aliens, but a profound testament to the human capacity for pattern recognition, a skill so powerful it sometimes sees signals in the noise, even when the signal is not really there. That sense of profound cold is another cosmic assumption we need to dismantle. The vacuum of space is not uniformly cold because empty space does not have a temperature in the way we experience it on Earth. Here, temperature is transferred through the air, a process called convection, or through direct contact, known as conduction. But in the void, there are no molecules to carry heat. Temperature becomes a personal matter, defined entirely by radiation. An object's fate depends on a single question: is it in the sunlight or in the shadow? Picture an astronaut on a spacewalk. The side of their suit facing the sun is being bombarded by the full, unfiltered power of solar radiation. With no atmosphere to scatter or absorb that energy, it heats up relentlessly, potentially reaching temperatures well over 200 degrees Fahrenheit. At the very same moment, the side of the suit facing away from the sun is exposed to the deep void, radiating its own heat away into nothingness. It would plummet to hundreds of degrees below zero. The astronaut is straddling an invisible line between scorching heat and deep freeze, protected only by their suit's sophisticated systems that work to balance these extremes. The moon provides the ultimate demonstration of this brutal duality. Its surface is a barren wasteland with no atmosphere to moderate the temperature swings. During the long lunar day, which lasts about 2 Earth weeks, the ground bakes under the sun's glare, reaching a blistering 260 degrees Fahrenheit, hot enough to boil water. But when the sun sets, the heat radiates away into space with astonishing speed. The same landscape plunges to 280 degrees below zero during the 2-week night, a temperature swing of over 500 degrees. This is the true nature of space, a place without medium, without moderation, where an object's temperature is a direct and violent negotiation between the raw power of a star and the absolute cold of the cosmic background. That brilliant tapestry of stars above us feels eternal, a constant and unchanging map of the cosmos, yet this too is an illusion of time and distance. Every single point of light you see in the night sky is a message from the past, a delayed transmission traveling across a void so immense that the very stars we admire may no longer exist. This is because light, for all its incredible speed, does not travel instantaneously. It moves at a finite pace, taking time to cross the cosmic ocean. The nearest star to our Sun, Proxima Centauri, is so far away that its light takes over 4 years to reach us. When you look at it, you are seeing it not as it is tonight, but as it was more than 4 years ago. This delay grows with distance. The bright star Sirius, the jewel of the winter sky, is a vision from 8.5 years in the past. The 7 sisters of the Pleiades cluster shine with light that began its journey 400 years ago during the age of Galileo. And the central bulge of our own Milky Way galaxy shows us a glow that is over 25,000 years old, from a time when the last ice age still gripped our planet. This leads to a profound and haunting possibility. Some of the most famous stars in our sky could have already met their violent end. Take Betelgeuse, the red giant that forms the shoulder of the constellation Orion. It is a massive, unstable star on the brink of collapse, a prime candidate for a supernova explosion. Astronomers know it could go off at any moment in a spectacular flash visible even in daylight. But Betelgeuse is about 650 light-years away. If it exploded tomorrow, we would not know for 650 years. It is entirely possible that Betelgeuse has already died in a cataclysmic fireball, and the news of its death is still traveling towards us, a wave of light carrying the story of its final moments across the centuries. The night sky is not a live broadcast, it is a grand cosmic museum, each star a fossil of light from a different era. You are looking back in time, watching a history of the universe unfold, one photon at a time. The stark blackness behind the Apollo astronauts is a silent mystery. If space is filled with countless stars, why does the lunar sky appear so utterly empty in those historic photographs? The answer is not a cosmic cover-up, but a simple lesson in camera mechanics. The challenge is one of dynamic range, the difference between the brightest and darkest parts of a scene. On the surface of the moon, the sun is glaring directly down onto white spacesuits and pale gray soil. This landscape is brilliantly illuminated, much like a beach on a cloudless noon. To properly expose this bright subject, a camera needs a very fast shutter speed and a small aperture, letting in just enough light to capture the details without washing everything out in a featureless white blob. The stars, however, are incredibly faint points of light. To capture them, you need the opposite settings, a wide open aperture and a slow shutter speed that lets light accumulate over seconds or even minutes. You cannot have both in a single photograph taken with standard settings. If Mission Control had configured the cameras to capture the stars, the picture of Neil Armstrong on the lunar surface would be a completely overexposed white rectangle, with the astronaut and the lunar module lost in a blinding glare. The stars were sacrificed to preserve the historic details of the mission itself. For definitive proof, we only need to look at other types of space photography. The Hubble Space Telescope specializes in taking those long-exposure images, staring at a single patch of seemingly empty sky for days to gather the faintest light. Its famous deep-field images reveal thousands of galaxies in a space the size of a grain of sand held at arm's length, each galaxy a swirling mass of billions of stars. Even from Earth's orbit, astronauts can and do take breathtaking pictures of the starry sky. When they photograph the International Space Station's exterior at night, using a long exposure, the structure is lit by Earthshine while the background explodes with the dense, brilliant band of the Milky Way. The stars were there all along, waiting patiently in the darkness for a camera that had the time to see them. But that emptiness is the universe's greatest illusion. The void between stars and galaxies is not truly void at all, but filled with two profound and invisible mysteries that dominate the cosmos: dark matter and dark energy. Think of the universe as a grand cosmic ocean. The stars, the planets, the galaxies we can see, all of it is just the faint, shimmering foam on the surface. Beneath that foam lies a vast, deep, and hidden reality. Together, dark matter and dark energy make up about 95% of everything that exists, leaving the familiar world of atoms and light as a mere 5%. We have been studying a cosmic shoreline, completely missing the ocean itself. So what is this hidden world? Dark matter is the universe's invisible skeleton. We cannot see it, touch it, or detect it with any of our instruments directly because it does not emit, absorb, or reflect light. Its presence is only revealed by its immense gravitational pull. We watch galaxies spin, and we see that the stars on the outer edges are moving far too quickly. According to the laws of gravity, these rapid speeds should fling the stars away into the void, tearing the galaxy apart. The fact that they stay bound means there must be an enormous amount of unseen mass holding everything together, a gravitational glue that we call dark matter. It forms a vast spherical halo around every galaxy, a scaffold upon which the visible universe is built. Then there is dark energy, an even stranger force. In the late 1990s, astronomers made a shocking discovery. They found that the expansion of the universe is not slowing down as everyone expected from the pull of gravity. It is speeding up. Something is actively pushing space apart, stretching the cosmic fabric faster and faster. This repulsive force, this cosmic anti-gravity, is what we call dark energy. It is the dominant influence in the universe today, an energy inherent to the vacuum of space itself that is driving galaxies to fly away from each other at an ever-increasing rate. To grasp this staggering imbalance, imagine a vast, dark forest at night. The entire forest is the cosmos. The ordinary matter we know, every tree, every leaf, every creature, is represented by a single lit match that you hold in your hand. The light of that match is everything we have ever seen or touched. The rest of the forest, the immense, overwhelming darkness surrounding you, is the realm of dark matter and dark energy. We are just beginning to understand that the true story of the universe is not written in the stars, but in the profound and invisible forces that command them. Even the rigorous training of an astronaut involves a carefully crafted illusion. The iconic image of trainees floating inside a padded aircraft, the so-called vomit comet, seems like a perfect rehearsal for life in orbit. Yet these simulations are brilliant approximations, not the real thing. That aircraft does not create zero gravity. It performs a specific aerial maneuver known as a parabolic flight. The pilot climbs at a steep angle, engines roaring, pushing everyone inside into their seats. Then, at the peak of the climb, the pilot reduces thrust and follows the curved path of a free-falling object. For about 20 to 30 seconds, the plane is in a controlled fall, tracing the arc of a parabola. Inside, everything and everyone is falling at the exact same rate, creating that precious sensation of weightlessness. It is a perfect, though fleeting, demonstration of the equivalence principle, the same physics that keeps the space station in orbit. But as soon as the pilot pulls out of the dive, gravity reasserts its pull, and the trainees settle back onto the floor, ready for the next climb. This cycle repeats dozens of times a flight, offering only minutes of accumulated practice in a state of freefall. For practicing the complex mechanics of a spacewalk, astronauts turn to water. They spend hours submerged in giant pools like NAS, a neutral buoyancy laboratory, wearing full spacesuits that are weighted to be neutrally buoyant. This means they neither sink nor float, but hover in the water, mimicking the feeling of being untethered from gravity. It is an excellent way to rehearse the slow, deliberate movements and tool handling required for exterior repairs, allowing them to practice for hours without the time constraints of a parabolic flight. However, water creates drag that true microgravity lacks, and the buoyancy, while close, is not a perfect match. The actual microgravity of orbit is a continuous state of freefall around the planet, a persistent condition that affects everything from fluid dynamics in fuel tanks to the way the human body adapts. These training methods are masterclasses in simulation, giving astronauts the muscle memory and procedural knowledge they need, all while their feet remain, at least intermittently, planted on Earth. The notion that humanity never reached the moon is a story built on shadows and misunderstandings. One of the most persistent claims points to the American flag, appearing to wave in a world without wind. But this motion was not a flapping banner, it was an artifact of inertia in a vacuum. The flag was mounted on a horizontal rod to hold it extended, a necessary feature since there is no air to fill it out. When the astronauts planted it, they twisted it back and forth to work the pole into the tough lunar soil. This action set the flag into a persistent, slow oscillation. With no air resistance to slow it down, that back-and-forth motion continued for much longer than it would on Earth, creating the illusion of a gentle, wind-blown wave in the video footage. It was not a breeze, but the ghost of an action preserved perfectly in the stillness of the moon. Another frequent question asks why the sky in the lunar photographs is a stark, starless black. We have already explored the camera science behind this, but it bears repeating for this specific context. The lunar surface was blindingly bright under the unfiltered sun. The astronauts' white suits reflected this intense light. To capture these historic details without overexposing the entire image into a white blur, the cameras were set with fast shutter speeds and small apertures, perfect for the bright ground but completely inadequate for registering the faint pinpricks of distant stars. The stars were always there, just too dim for the film to record under those specific settings. The most definitive proof, however, lies not in explaining away shadows, but in physical artifacts left behind and observed from Earth. The Apollo missions placed laser-ranging retroreflector arrays on the surface, essentially sophisticated mirrors designed to reflect light directly back to its source. For decades, observatories on Earth have been firing lasers at these precise locations on the moon. They measure the exact time it takes for the light to make the round trip, a measurement so precise it has allowed us to track the moon's orbit receding from Earth by about 1.5 inches per year. This is not data that can be faked. It requires a physical, human-placed device sitting on the lunar dust. More recently, the Lunar Reconnaissance Orbiter has circled the moon, mapping its surface in breathtaking detail. Its powerful cameras have captured images of the Apollo landing sites themselves, showing the distinct descent stages of the lunar modules, the trails of astronaut footprints, and even the discarded science packages, all exactly where the mission logs said they would be, resting silently in the fine gray soil for half a century. These are not claims from a single government or a single photograph. They are multiple, independent lines of evidence, from laser physics to orbital imaging, all converging on the same undeniable truth. The flag did not wave, the stars did not appear, and human beings absolutely walked on the moon. Our own star's true nature is hidden behind a simple, fiery word. The sun is not a ball of fire. Fire is a chemical reaction, a process of rapid combustion that requires fuel and oxygen, and the vacuum of space provides neither. The sun is something far more powerful and fundamental, a colossal sphere of incandescent plasma. Plasma is a fourth state of matter, a superheated gas so energetic that its atoms are torn apart, leaving a swirling soup of atomic nuclei and free electrons. This seething ocean of charged particles is the true substance of our star, and its energy comes from a process that dwarfs any chemical burn, nuclear fusion. Deep within the sun's core, the heart of this plasma sphere is a cosmic furnace of unimaginable pressure and temperature. The pressure is so immense, over 200 billion times the air pressure we feel at sea level, that it forces the nuclei of hydrogen atoms to overcome their natural repulsion and slam into one another. In a series of steps, these collisions fuse 4 hydrogen nuclei together to create a single, new nucleus of helium. But here is the crucial part. The mass of that single helium nucleus is slightly less than the total mass of the 4 original hydrogens. That tiny bit of leftover mass does not just vanish. According to Einstein's famous equation, it transforms directly into a staggering amount of pure energy. Every second, the Sun's core fuses over 600 million tons of hydrogen into about 596 million tons of helium. The missing 4 million tons of mass is converted into energy, the brilliant light and heat that sustains our entire solar system. This energy does not rush straight to the surface. It begins a slow, epic journey outward through two distinct zones. First, it passes through the radiative zone, a region so dense that photons of light are absorbed and re-emitted by atoms in a random walk. A single photon might take over 100,000 years to zigzag its way through this thick interior. Finally, the energy reaches the convective zone. Here, the plasma behaves like a boiling pot of water. Vast currents of superheated gas rise to the surface, release their energy as light and heat, then cool and sink back down to be reheated, creating a continuous, churning cycle that we see as the Sun's grainy texture or granulation. So the next time you feel the Sun's warmth, remember you are feeling the echo of a nuclear reaction that began in the core hundreds of millennia ago, a testament to the universe's ability to build entire worlds from the ashes of lost mass. One of the most persistent doomsday stories whispers of a phantom world, a hidden planet called Nibiru, supposedly on a catastrophic collision course with our own. This terrifying idea has haunted the fringes of astronomy for decades, yet it is a myth built on a total absence of evidence. Our solar system is not hiding a massive, rogue planet in its inner reaches because our modern sky surveys would have found it long ago. Consider the power of missions like NASA's Wide-Field Infrared Survey Explorer, or WISE. This telescope was specifically designed to scan the entire sky in infrared light, perfect for detecting the faint heat signature of cool, dark objects that visible light telescopes might miss. If a planet large enough to threaten Earth, perhaps several times the mass of our own, were lurking in the space between us and the asteroid belt, its thermal glow would have been an unmistakable beacon in WISE data. The mission completed a full sky scan with sensitivity so high it could find a Jupiter-sized object over 4 times farther away than Neptune. After meticulously analyzing years of data, astronomers can state with certainty that no unknown object of that scale exists within the vast territory of our own solar system. The myth itself originated not from any scientific observation, but from the writings of a single author who claimed to translate ancient Sumerian texts, weaving a tale of a planet with a long, elliptical orbit that periodically swings through our inner solar system. This story was then adopted and amplified by various pseudoscientific and conspiracy theory circles, often tied to predicted dates of apocalypse that have come and gone without event time and time again. The reality is that the gravitational pull of such a massive world would have visibly perturbed the orbits of every other planet, an effect that our precise planetary tracking would have detected centuries ago. The silence of our telescopes and the stability of our celestial clockwork offer the most powerful rebuttal. The cosmos is full of genuine wonders and mysteries, but a doomed planet named Nibiru is simply not one of them. That same emptiness that hides the stars in photographs also creates a profound and perfect silence. In the vacuum of space, no one can hear you scream, and this iconic movie line is one of the most scientifically accurate statements ever made in science fiction. Sound, as we experience it, is a mechanical wave. It is not a form of light or energy that can travel on its own. It is a physical vibration, a series of compressions and rarefactions that must travel through a medium, a substance made of molecules like air, water, or solid metal. These molecules bump into each other, passing the vibration along in a chain reaction that eventually reaches our eardrums. Space, however, is a near-perfect vacuum. It is emptier than any vacuum we can create on Earth. There are simply not enough molecules present to bump into each other to carry that vibration. A supernova, the most violent explosion in the universe, can rip a star apart with the force of octillions of nuclear bombs, yet it would not make a whisper if you were floating nearby. The cataclysm would be utterly, completely silent. This does not mean the cosmos is devoid of vibration, however. Scientists have found a brilliant way to listen to the universe by translating its non-audible data into sounds we can hear, a process called data sonification. Space is filled with magnetic fields and clouds of charged particles known as plasma. While these plasmas cannot carry sound waves in the traditional sense, they can carry waves of electrical and magnetic energy. Spacecraft like NASA Van Allen probes have recorded these ripples. Scientists then take these recordings, which exist as patterns of data, and shift their frequencies down into the range of human hearing. The churning plasma waves around Jupiter, for instance, become eerie chirps and whistles. The vibrations in the magnetic field of Saturn are transformed into a haunting interstellar chorus. These are not sounds traveling through space to a microphone. They are a translation, a way for us to experience the hidden rhythms of the cosmos with a different sense, turning the dance of invisible forces into a symphony we can finally hear. It is a powerful reminder that while the universe may be silent, it is far from quiet. That hazy river of light arching across the night sky is not a distant cloud of cosmic dust. It is our home, seen from the inside. We are living within the Milky Way galaxy, and that soft glow is the combined light of countless stars in the galactic disk, a structure so vast we can only perceive it as a band when we look edge-on towards its crowded center. Picture our galaxy as a colossal spinning city of stars, a barred spiral with immense arms winding out from a bright central hub. Our solar system is not at the center of this metropolis, but nestled within one of its quieter suburban streets, the Orion Spur, about halfway out from the brilliant downtown core. From our position, when we gaze towards the constellations of Sagittarius or Scorpius, we are peering directly into the galaxy's bustling, densely packed center, a region dominated by a massive bulge of ancient stars. This central bulge is a spherical swarm of stellar giants, a relic from the galaxy's earliest days. Looking in the opposite direction, out towards the constellations of Perseus or Auriga, we see the sparser outskirts of the disk where the stellar population thins out into the galactic hinterlands. The scale is almost incomprehensible. Our entire solar system, from the Sun to the distant Oort cloud, is a single speck within a disk that contains between 100 and 400 billion stars. Each of those stars could be a sun to its own worlds, each a potential island in the great dark ocean. Our Sun takes about 230 million years to complete one full orbit around the galactic center, a journey so long that the last time we were in this position, dinosaurs were just beginning their reign on Earth. That gentle band of light is not a backdrop, it is the walls and streets of our own cosmic neighborhood, a reminder that we are not just looking at the universe but are deeply, permanently embedded within its grand design. That streak of light you call a shooting star is not a star at all. It is a cosmic grain of sand meeting its fiery end. The poetry of the night sky gives us beautiful names, but the science reveals a more precise and equally wondrous story. It all begins with a meteoroid, a small fragment of rock or metal drifting through the emptiness of space. These particles can be as tiny as a speck of dust or as large as a small boulder, the leftover crumbs from asteroid collisions or the dusty trails abandoned by comets. When Earth, on its own journey around the Sun, plows through one of these clouds of debris, the meteoroids are swept up by our atmosphere. Traveling at tremendous speeds of tens of thousands of miles per hour, they violently compress the air in front of them, heating it to a blazing incandescence. The brilliant streak of light you see is not the rock itself burning, but the superheated air glowing along its path. At this moment, the particle earns a new name, a meteor. Most of these interplanetary visitors are so small they vaporize completely dozens of miles above the ground, leaving nothing but a fleeting, luminous scratch on the night. But sometimes a larger chunk survives the inferno. If any part of the original meteoroid makes it through the atmosphere and lands on Earth's surface, it is given a third and final title, a meteorite. This is a rare piece of another world, a tangible rock you can hold in your hand. The most reliable and spectacular displays are our annual meteor showers, like the Perseids in August or the Geminids in December. These are not random events, they are celestial anniversaries occurring when Earth's orbit crosses the specific debris trail left behind by a comet. As a comet orbits the sun's heat loosens ice and dust, scattering a river of particles along its path. When we pass through that river, thousands of these tiny meteoroids enter our atmosphere at once, creating a shower of silent, cosmic fireworks. Each flash is the final message from a piece of a comet that may have last visited the inner solar system centuries ago, a final, brilliant spark from a long-vanished traveler. Jupiter's immense size has earned it a misleading nickname, a failed star, suggesting it almost ignited into a second sun for our solar system. This idea paints a dramatic picture, but it fundamentally misunderstands the cosmic chasm between a planet and a star. The defining characteristic of a star is not its size, but the raging nuclear furnace in its heart. Stars like our Sun are so massive that their cores experience unimaginable pressure and temperature, forcing hydrogen atoms to fuse into helium and releasing colossal energy. Jupiter, for all its grandeur, falls dramatically short of this benchmark. To cross the threshold from gas giant to even the smallest category of star, a red dwarf, Jupiter would need to be at least 75 to 80 times more massive than it is today. Its current composition is primarily hydrogen and helium, the same ingredients as the Sun, but it simply does not have the gravitational weight to crush its core into a state of sustained fusion. It generates some internal heat, yes, but this comes from the slow compression of its own material and the release of primordial heat left over from its formation, a far cry from the self-sustaining power of a true star. Jupiter and the Sun represent two entirely different cosmic destinies born from the same protoplanetary disk. The Sun gathered the vast majority of the material, becoming the system's anchor, while Jupiter coalesced from the leftover gas and dust, becoming its largest and most influential planet. Its powerful gravity shapes the asteroid belt, protects the inner planets from frequent comet impacts, and shepherds a family of dozens of moons. It is not a failed star, but a spectacularly successful planet, a testament to the diverse outcomes that are possible when a solar system is born. Our own planet's shadow has been wrongly accused for the Moon's beautiful monthly transformation. The slow dance from a slender crescent to a brilliant full moon is not a story of Earth blocking the Sun's light, but one of perspective and illumination. Think of the Sun as a brilliant spotlight shining on a perfectly round gray ball. That ball is the Moon, and we are sitting here on Earth watching it from the side. The Moon does not produce its own light, it only reflects the Sun's rays. As the Moon circles our world every 29 days, we see a different fraction of that sunlit half. When the Moon is positioned between Earth and the Sun is lighting up the side facing away from us. From our viewpoint, the Moon is virtually invisible, a new moon lost in the Sun's glare. A few days later, the Moon has moved along in its orbit, and we begin to see a thin sliver of the sunlit side, the waxing crescent. A week after the new moon, it has traveled a quarter of the way around us. Now we see exactly half of the Moon's day side and half of its night side, creating the first quarter phase. The journey continues, revealing more and more of the illuminated face until, when the Moon is on the opposite side of Earth from the Sun, we see the entire day side in its full glory. Then the cycle reverses, waning back to a crescent and finally to new again. This cycle of phases is a continuous, gentle process of revelation and concealment. A lunar eclipse, however, is a specific and dramatic celestial event. It can only happen during a full moon, but not at every full moon. For an eclipse to occur, the Sun, Earth, and Moon must be in a near-perfect straight line. Earth casts two shadows, a faint outer penumbra and a dark central umbra. During a lunar eclipse, the full moon glides first into the penumbral shadow, dimming slightly. The real spectacle begins when it starts to move into the umbra, Earth's deep central shadow. This is when we see the familiar coppery red bite appear on the moon's edge. If the alignment is perfect, the entire moon slips into this shadow, but it does not vanish. Sunlight filtering through the ring of Earth's atmosphere is bent or refracted onto the lunar surface, staining it with a dim, eerie, reddish glow. The entire event is relatively brief, lasting a few hours at most before the moon moves out of the shadow and its normal bright face returns. So the phases are a constant, gentle cycle of light and shadow dictated by orbital position. An eclipse is a rare and precise alignment, a momentary interruption where Earth's shadow falls directly upon the lunar surface. One is a monthly rhythm of changing perspective. The other is a cosmic game of shadow tag that requires perfect timing. The silence of the cosmos is not an answer, but a question we are only just learning to ask. For all of human history, the idea that we might be utterly alone in the universe has felt like a terrifying possibility, a profound isolation in an infinite sea of darkness. Yet this belief in our solitary existence is less a scientific conclusion and more a myth of certainty, one that modern astronomy is systematically dismantling. The numbers themselves tell a story of overwhelming probability. Consider the Drake equation, a framework devised by astronomer Frank Drake, not to find a single answer, but to outline the factors involved in the potential for communicative civilizations. It multiplies the rate of star formation by the fraction of stars with planets, the number of planets that could support life, the fraction where life actually emerges, the fraction where that life becomes intelligent, and so on. Plug in even the most conservative estimates for each variable, and the result is not zero, but a galaxy that should be teeming with potential. The real revolution has come from the discovery of exoplanets, worlds orbiting other stars. We now know that planets are not rare anomalies, but the common outcome of star formation. Our Milky Way galaxy alone contains billions of stars, and a significant percentage of them host planets residing in the habitable zone, that Goldilocks region where temperatures could allow for liquid water to exist on a rocky surface. Each of these worlds is a fresh experiment, a new potential cradle for life. This staggering abundance of real estate stands in stark contrast to the eerie quiet, a puzzle famously known as the Fermi paradox. If the universe is so vast and so old, where is everybody? The solutions to this paradox are as numerous as they are thought-provoking. Perhaps intelligent life is exceedingly rare, or its technological phase is tragically brief. Maybe they are out there, but their methods of communication are so advanced we cannot yet recognize them, or they are simply choosing to observe us in silence. The Great Filter hypothesis suggests there may be an evolutionary or technological barrier that nearly all life fails to pass, a sobering thought that places our own future in question. The silence is not evidence of absence, it is a challenge. Scientists are actively listening, scanning the skies with projects like SETI, the search for extraterrestrial intelligence, analyzing radio waves for any pattern that betrays an artificial origin. Others are peering into the atmospheres of distant exoplanets with powerful telescopes like the James Webb, hunting for biosignatures, chemical imbalances that could only be sustained by biological processes, such as the simultaneous presence of oxygen and methane. Finding a single microbe on a distant world would irrevocably transform our understanding of the universe and our place within it. We are living in the generation that may finally shift the answer from a philosophical speculation to a scientific discovery. The cosmos holds its secrets close, but we are just beginning to learn how to listen. We have journeyed through a gallery of cosmic illusions, from the color of our sun to the silent reality of the void. Each of these 30 debunked myths reveals a simple but powerful truth, that our universe is far more complex and fascinating than our assumptions would have us believe. Science does not strip away wonder, it replaces fantasy with a reality that is deeper, richer, and infinitely more compelling. The true nature of a black hole is more intriguing than any vacuum cleaner, and the real story of human survival in space is more harrowing than any explosion. This process of questioning, of testing old ideas against new evidence, is the very engine of discovery. It is how we push back the boundaries of ignorance and chart the vast, beautiful, and often strange cosmos we call home. So keep looking up and keep questioning what you think you know. The next great revelation is waiting just beyond the horizon of your current understanding. If you enjoyed this journey from myth to reality, subscribe for more content that explores the incredible truths of our